All right, so yesterday we talked about kinetics. Today we're going to talk about the rate law. Really quickly, yesterday I talked about this nasty equation. And this is what this nasty equation does. It ties all of the tenets that affect rate that we talked about yesterday, effective collisions, we talked about activation energy, and we talked about temperature, and it takes all of that into account in this constant called the rate constant. Okay, one more time, you should look at the Arrhenius Pencast to get all of this down. And so this rate constant is part of the rate law, and the rate law is what we're going to study today. So if K, the constant, has a big value, it's a fast rate of reaction. Likewise, if K has a small value, it's slow. And this value is determined by these variables. Okay, so the rate law that we're talking about today is called the differential rate law. I'm the only person who really makes a difference between the two rate laws, but it helps me keep it straight. The differential rate law is an equation that relates the rate of reaction to the concentration of the reactants raised to some power. So another way to think of the differential rate law is how is rate affected when concentration changes. All right, and we need a rate law for a couple of reasons. If you want something to happen, it would be very nice to be able to see how fast it's going to happen. You don't want a rate of reaction that is millennia long. You want one that you can actually visibly see. It's useful in postulating the mechanism of a reaction. Here's an FYI for you. Most reactions, here is the standard reaction I use to explain everything. A plus B yields C plus D. It turns out that it probably doesn't happen in one step. It usually happens in a series of steps that's called the mechanism of the reaction. So a lot of times you'd like to know what intermediaries are being formed in case they're bad. And it's useful in classifying reactions into orders. Okay, so a rate law ignores the products. A rate law only has the reactants. Okay, so because only the reactants are involved, we need to examine the reaction when there are no products, and that is a nanosecond, or as fast as we can determine, after the reactants are mixed. You remember yesterday, if we looked at that graph and the reactants decrease in a nonlinear way. So the only time that we really can do this is at an instantaneous rate. So our instantaneous rate is as close to time equals 0 as possible. Okay, so differential rate laws tell the relationship between concentration and rate of reaction. Obviously, I think this is kind of important. For our general equation, A plus B yields C plus D, the rate law has the form of this. The initial rate is equal to the rate law constant times, remember that the brackets denote concentration and molarity, the concentration of A raised to some power m times, write yourself a note right here, this is multiply times the concentration of B raised to some power. Right, here are the things that kids get bumfuzzled with. These exponents, m and n, are not the coefficients from the balanced equations. They are not. Here's the other thing. The value of k and these exponents are only determined experimentally. You'll ask me in about 10 minutes, how did you know that? I knew because I looked at the experiment. Now, K does not depend on the concentration. You can tell because in this equation, there is no concentration. However, it does depend on temperature and activation energy. Okay. Here is a little vocab for you. The reaction order is that exponent in the rate law. Okay, if I were to have a reactant A, and I wanted to talk about its order, and if there was a 1 there, I would say the order of A is 1. If I had a reaction that had the rate law that looked like this, I would say the order of B is 2. If I wanted to know the overall order, I would add 1 plus 2, and I would say the overall order for the reactants is 3. So here is a reaction, the formation of water. The rate at which this will occur is equal to the rate law constant for this reaction times the concentration of H2 raised to the first power. I could tell it was raised to the first power because I'm a lazy chemist and I don't write ones, times the concentration of O2 raised to the first power. So overall, it's second order. Experimentally, for this equation, somebody found that this is first order in HCl, second order in NH3, so overall it is third order. What do order and rate have to do with each other? Okay, if the order of a reactant is 1, or the reaction is 1, let's say we have A is our reactant, and it's first order. If I double the concentration of A, then the rate will also double. If the order of the reaction or the reaction is 2, if I double the concentration, then the rate will quadruple. All right. Now, if I had a reactant that was 0 order, what that means, if I double the concentration, there is no change in rate.
What does the order even, like, I'm still confused on what.
Okay, here's why you would need this. Let me find a piece of paper. Okay, here's a rate law constant. Let's say that you want this reaction to occur faster.
Yeah.
Okay, would you add more A or more B?
More B.
More B, because you know its overall order is 2 here, so you would get this reaction to occur faster by doubling this rather than that. That's why you use it.
But if you double B, then you still have the same amount of A, and then that becomes like a limiting reactant kind of thing.
Yeah, that would be part of it, but if you were taking just the rate in isolation and look at it, that's what you would do, assuming that you've got enough not to completely limit this one immediately. Okay. Now, let's move to the rate constant and its big deal. I am not in charge of this. I didn't think it was a tricky thing to do. I just teach you what you need to know. The rate constant stays the same except when the temperature changes. The big deal about the rate constant is this. The rate constant has a magnitude, which is a number, and it also has a unit. AP likes to give you multiple choice questions where they give you a rate law constant, and they tell you you need to know the order of that overall reaction just by and the only way to solve that problem, the only way to answer the question, is to know that the unit gives you a clue to the order of the reaction. Oh. So, a rate constant usually has a unit that has some concentration per unit time. All right. So the concentration is going to be in molarity, and we recall that molarity is moles per liter. So this is how I want you to use this formula to determine what the rate constant is based on the order of the reaction. So the molarity, 1 minus the order of reaction, times the time unit, whatever it is, to the -1 power, will give you the unit for the rate law constant. Okay, that's not helpful. Here we go. Let's say you have a 0 order reaction, and you would take 1 minus 0, which would be m, times the time interval. Most rates are measured in seconds, raised to the -1 power. That would be the same. Seconds to the -1 power is the same as saying 1 over seconds. Tying it back into right there. Okay. If you have a first order reaction, 1 minus 1 is 0. So the molarity doesn't even appear in the unit for the rate law constant. If you have a second order reaction, 1 minus 2 is -1 times second minus 1. I kind of think it's nitpicky, but it shows up in almost every single AP exam. Okay, let's look at the 2 sample questions that you were given. What's the overall order for the following reaction? 3. 1 that's not written plus 2 is? What would be the unit for the rate law constant for the following rate laws, assuming that the rate, it would be in molarity per second? Okay, the overall order of this reaction is? So it would be molarity 1 minus 3 times second to the -1, which resolves to
Can you just write it over seconds?
yeah. Yep. You know what? Nobody in the history of our AP classes ever lost the point for not having the unit for the rate law constant. In fact, used to be, you just had to memorize these. And I was not having a life, surfing the internet, and I found that formula for you. And I was at an AP conference, I think it was 2 years ago, and the guy was talking about, well, you just have to do this. Memorize these. And I said, well, you could use this equation, and I'm not kidding, got a standing ovation because chemistry teachers I like that, and I'm not going to kid you either. I took full credit for the whole thing. Told everybody I thought it up. I didn't. Okay, so what would be the unit here? Dunsky. All right, now I'm going to do what?
Why is it -1?
Because the overall order here is 2. So it would be 1 minus 2. Got it?
So do you have to write it like that with the exponents, or can you like say 1 over?
1
You can, you know what, you can do this 1,000 different ways. This is the easier way to do it. This is the same as this, which is the same as this. I mean, I don't care. Personally, I think this is way easier.
Yeah.
Okay. So, I am going to make you do these the old-fashioned long way. I'll get it in a minute. Because I said. Now, because they get harder faster, and I want you to be able to do all of these all the time. I would like you to write down somewhere these directions on how to do these. First of all, before you write this down, these are experimental initial rates for the reaction A plus B yields some products. So what is happening here is the scientist is saying, okay, if I take 0.1 molar A and mix it with 0.1 molar B, and I determine the rate. And I determine the rate is 2 times 10 to the negative third. Now I'm going to double the amount of A, keeping the amount of B constant, and I'm going to see what happens to the rate when I change this concentration. It doubles. Now, for trial 3, the experimenter said, I'm going to keep the concentration of A steady while I double the concentration of B, and I'm going to see what happens when I change B to the rate. Okay? So only from this data can I get the rate law with the orders of each one of the reactants. I need to find the order of A, and I need to find the order of B, and I can also figure out what the rate constant is. And the way I'm going to do that is I need to choose an experiment to evaluate. And the experiment that I need should have one variable that changes and one variable that does not change. Then I'm going to compare the complete rate law of those two experiments. And I'm going to put the larger numbers on top because I like things to be easy. You'll see.
You got to go.
Following you? The game here?
Maybe. Okay, here we go. Now, the rate law for this experiment, I'm going to write what I know. The rate law is going to be the rate is equal to the rate law constant times the concentration of A raised to some power times the concentration of B raised to some power. Now what I'm going to do is use all the information given and just compare some numbers and see what I come up with. So I need step 1 to evaluate A. I want A to change, but B to remain the same. So it's just the change in A that's reflecting the change in the rate. So I'm going to try trial 1 and 2. I'm going to put 2 on top because it's a bigger number. Trial 1 on the bottom because it's a smaller number. And then I'm just going to insert numbers into this equation, into this rate law as much as I can. I know the rate, 4 times 10 to the negative third, is equal to the rate law constant times the concentration of A, 0.2, raised to some power, times the concentration of B, raised to some power. I'm going to compare that to trial 1, where the rate is 2 times 10 to the negative 3, equal to K, the rate law constant that I have not determined. This time A is 0.1, raised to some power, and B is 0.1, raised to some power. Now that could be ugly until we see that this cancels and this cancels. Resolving this, we have 2 is equal to 2 raised to some power. It is intuitively obvious that m is equal to 1. So the order for A is 1. Now I need to figure out what the order of B is. So in order to do that, I would like to find 2 experiments where A remains the same, but B changes. This very helpfully will be 3 and 2. Will it always be like that? No, sometimes there will be 6 experiments and you're all over the place. Tomorrow, there will be one where nothing is kept constant. That could be painful. Okay, so we decided trial 3 and trial 2. So trial 3 is a rate of 16 times 10 to the negative third is equal to the rate law constant times 0.2 raised to the first power. I will write it just because we're new at this. Times 0.2 raised to some power we've yet to determine. 4 times 10 to the negative third is equal to k. All right, this time this cancels and this cancels. 4 is equal to 2 raised to the second power. This one too is easy to determine. It's 2. If you had trouble, if you would like to rely on some math to figure this out, n is equal to the log of 4 over the log of 2. So you can mathematically figure it out. So that means that B is second order. So we've done all of this work just to find the exponents in the rate law. So now we have rate is equal to A, which is first order, times B, which is second order. This is the rate law for this equation. Now, they want us to determine the value of the rate law constant. If I take the rate law and rearrange it to solve for k, k is equal to rate oops. Here we go. Now I can take the values from any experiment that I would like and figure it out. I'm choosing experiment 3. K is equal to the rate from experiment 3 over the concentration of A from experiment 3 raised to the first power times the concentration of B from the third experiment raised to the second power. K is equal to, somebody do big math, 2. All right. The math part's easy. Now you need to figure out what the unit for the rate law constant is. And you need to inspect the rate law to do that. Overall order for this is 3. So, molarity 1 minus 3 is, okay, the time value here is seconds. This is the rate law constant. Okay.